Good morning, everyone. Today is 16th of November. It's our last final lecture on our course, Power Electronics, Introduction to Power Electronics and Solutions. We had a very nice and successful semester. The classroom is full, and today we have presentations. The master students, they will have only to upload their report, but we have here two PhD students who decide to make a presentation, and they are also writing a paper formatted in accordance with TPOE. So I would like to invite those students for their presentations, and then we will conclude our course. Thank you very much. It was a pleasure to be your instructor for this course. So the first presentation will be by Peyman. I'll just share the screen and he is coming here so he can start. Okay, so here is your presentation. You can start and go on.
No. I choose this paper entitled Stabilizing Model Predictive Control for Voltage Regulation of DC-DC Boost Converter, which has been published in IEEE Transaction Control System 2014. Author in this paper proposed a cascade voltage control strategy for this DC boost converter with MPC model predictive control in the inner loop. As you know, a PI controller is a famous control for voltage regulation of this DC boost converter, but it has several drawbacks and also limits converter performance. For example, in the PI controller structure, we ignore all our physical constraints and on the inputs and also state variable. On the other hand, we assume that converter behavior is linear behavior, but in fact, it is nonlinear. And we should consider these properties of converter in the control procedure. In model predictive control, signal control comes out from optimization procedure over finite number of feature time steps. Then we can exactly consider physical constraints and also nonlinear behavior of converter in the control procedure. Here you can see cascade control strategy block diagram and also DC-DC boost converter circuit equivalent. As you know, here we use two control block of one controller, PI controller in outer loop for voltage control, and also in the second, in the inner loop, we use MPC controller for current control in the inner loop for DC converter. As you know, reference value of MPC controller for inductor currents calculated from a PI controller, and also signal control for this boost converter comes from MPC controller. For a simulation of this cascade control strategy, we have to extract a state equation of this DC boost converter. Here we calculated all of the state equation of the boost converter, and consequently we rewrite in discrete state equations in the model predictive control. We use these equations in optimization procedure of MPC controller. Here you can see the objective function and also optimization problem of MPC controller for DC boost converter, which we should solve this problem in two separate modes: constraint mode and also unconstrained mode. In unconstrained mode, we calculated feasible signal control like these equations, and also in the constraint mode, we should consider limitation of 4 current inductor and also voltage capacitors. Here you can see my overall symboling of simulations, and you can see there are two main block functions. The first one is MPC controller, which we should put all of calculation of MPC controller and also optimization problem here in this block. And also in the DC-DC boost converter, we should put all of state equations of the DC-DC boost converter. As you know, a PID controller calculates reference value of MPC controller for inductor currents, and also output of MPC controller used for inputs for the DC-DC boost converter state equations. We will run this block diagram in two separate modes, constraint and also unconstrained mode. Here you can see the results in unconstrained mode. In the first second, we change the voltage reference from 67 volts to 100 volts. And as you can see, the controller can easily smooth and also track the voltage reference exactly. And also in this constraint mode, we consider this limitation for current and also voltage capacitor, and the controller correctly track and also smooth the voltage and also current inductors. It is my final presentation. Yes.
All right. Thank you very much, Peyman. So I have a question for you.
Okay.
Can you please tell me, for example, what is the importance of this course for you in your PhD, and how, when you compare, when you just started to what you are, how you are better prepared, and how you feel that this final project was important for you?
Yeah. MPC controller is very famous in the control issue. And I learned MPC concept and also converter control in this course. And also I learned how can I control this in boost converter and simulation of MPC control. And also I wanted to simulation with a symbol simulation.
Thank you, Peyman. So you believe you are better prepared now to do research in power electronics? Do you believe you are better prepared now to do research in power electronics?
Yeah.
Thank you. Thank you very much.
Thank you.
So I would like to invite our next presentation. And probably you are not doing presses, so I will remove this. I'll just give a quick pause here in our recording. Stop sharing. Okay. We are recording. So Qudrat is our next one to present. Can you please come? Are you presenting from your computer, or can you access?
I want to connect my USB there. It will be better idea.
Okay. So I will pause a little bit this recording. And okay, so now we have a presentation by Qudrat Ula, and sharing the screen. So you can now come here and okay, I put in slideshow from beginning. Okay, go ahead. Talk loud so we can record you.
First of all, thanks to all of you for being here. And thank you, Professor, for giving me an opportunity to present a final project about introduction to power electronic solutions. My name is Qudrat, and our teacher about power electronic solution is Professor Marcelo. So first of all, I would like to say that The title of this presentation is about SMC based single inductor based DC-DC converters to handle bidirectional power flow. And the table of content for this presentation includes introduction about this topic and why we selected this topic and the other available solutions related to bidirectional power flow of converters. And then we have a comparison of some topologies, and after that the reasons for this topology selection and switching pattern of MOSFETs, which are basic component of converters. And then we will see different control signals for different operating modes, because this is a synchronous 4-switch buck boost converter. So we will be seeing deriving formulas are for duty signal or control signal, which is also called control signal for MOSFET switches for both directions, like left to right and from right to left for step up and step down operations. So at the end, I will conclude this presentation with some simulation results which we have done. First of all, it is necessary to know that why there is use for DC-DC converters which should have a bidirectional power handling capability. The reason is that, as we can see in this figure, there are different things like modern LED lighting, telecommunication applications, which are mostly related to data centers as well. Office equipments, which are like mostly used in any office of any industry or organization, and photovoltaic panels, which are widely being used from the last 2 decades. Particularly, there has been significant rise from the last 10 years. And energy storages, which are like batteries or supercapacitors and these things, and other devices which are steadily being used in for camping accessories and sailing boats. For camping accessories, usually the tourism places are majority of the tourism places are located away from cities, and there might be lack of electrical networks, so we can use these converters with our vehicles and these things. So the need for these converters is basically a demand for modern life nowadays, because most of these applications are using DC current, so all these things require DC-DC converters. And they also require some applications need more than 50 volt, more than 55 volt, or up to 80 volt. And some applications require 5 volt to 24 volt, or up to less than 48 volt. So there is a standard from April, I think, which they have introduced, that the DC link voltage or DC input voltage can be considered as a 48 volt in DC current applications. And there is when there are being more research in this regard about the being standard of DC voltage as an input voltage. So there is a need of universal converter which should handle all these applications which I mentioned earlier. Which should have also the capability for bidirectional power flow, that if we need to charge our batteries or discharge our batteries, that can be used, or if we need to use those the voltage or current for our other purposes, then we can also use them as a converter, as an interface. So different eligible sorry, just a minute, it is here. So when we observe different eligible non-isolated bidirectional DC-DC converter topologies, there is a flyback topology and Z-type topology And there is also one other topology which is called Cook, or sometimes it is called Chuk topology. Professor, may I know how much time I have? Okay, thank you. And Cook topology. So in Cook topology is actually negative output converter, while CPEC or zeta topology is a positive output converter. Similarly, this is half bridge topology for 4-switch buck boost converter, in which there is single inductor is used for all charging and discharging and these things. Then we have on the left side, we have a setup for power flow from left side to right side, and similarly we have we can have a source and a load on the right side as well as on the left side as and this using this topology. So there is comparison for some topologies like flyback topology is inverting, Cook or Chuk topology is inverting, in which output voltage is inverted, but zeta and FS 4-switch buck boost converter topology is non-inverting. And their maximum voltage also can be found from these formulas. But the converter which we designed is up to 80 volts. So there is also some comparison for passive components and active components of these converters. As we can see that 4-switch buck boost converter has less number of passive components, so it means that the switching losses will be significantly reduced as compared to other topologies, which can handle bidirectional power flow. There are some few reasons which I found from literature to select all these topologies and to make a comparison. The voltage gain is lower than other power converters using flyback topology, but the cooked converter topology is better than flyback topology for ripple voltage and waveforms of current at the output side. The main important thing about cook converter is that coupling capacitor shifts energy from grid side by electromagnetic conversion to the load side. Similarly, CPEC converter can have better results in terms of efficiency as compared to flyback or cook topology. But the recent research shows that better voltage regulation can be achieved using 4-switch buck boost converter topology, as it has lower number of passive components, and this can be more useful for low power applications, power supplies, or PV panel applications. So switching pattern of MOSFETs for different operations from left to right during boost operation of the converter, switch 1 is always turned on and switch 2 is always off, while switch 3 is we are giving a controlled signal, which is also called duty signal, to switch 4, and switch 3 works as a complementary switch to the switch 4. Similarly, we can also have written a switching pattern for left to right, for buck operation and boost operation from right to left, and buck operation from right to left direction. So how we can shift power from left side to right side or right side to left side? Actually, I have used in Simulink this circuit we can see, in which this is actually a control switch in which first and third input ports are data ports, which we feed data to them, and in the center, the central port, which is second port, is a controlled port in which when we put when we give a signal of 1, then it transfers power from left to right, and when we give 0, it transfers power from right to left. On both sides, we already have in the Simulink we have connected DC voltage source and resistor, but it can be in it is dependent upon us that which direction we want to use, seeing the scenario available there. So control signal of boost mode from left to right. During the step up stage of the power converter, S1 is always on and S2 is always off, as I earlier discussed. The flow of inductor current can be seen in this figure. This figure is necessary because without this we cannot see the steady state behavior of the converter. In this way, we can find the steady state converter of the steady states of the converter states of the converter, and we can drive control signal, which is used as a gate signal or switching signal for the MOSFETs. So in this, this is basically double integral sliding mode controller. Why we are using this one? Because as my colleague Peyman earlier mentioned, that power electronic converters are basically non-linear in nature. So PI controllers or other linear controllers are still used, but in them they have little bit slower response, and steady state error is a little bit higher as compared to when we design a non-linear controller for such converters, then the response is better. We can see a quick dynamic response. At the same time, we can have minimum steady state error. So we have further used in this work double integral to reduce the steady state error, so that we can have minimum steady state error in our applications. So basically, first of all, for sliding mode controller, sliding surface is designed. In sliding surface, we use different tracking errors are tracked, which we have calculated, denoted by E1, E2, E3, E4, or they can denote by any other variable like X1, Y1, anything. So in this way, we have derived a control signal, which you can see here, which is fed to the MOSFET of the converters. So similarly, we can find a control signal for buckboard for left to right power flow. Using I will not go into details, as I have already told different tracking errors and these things. So I have mentioned here the final equation which we derive from mathematical. Some people say that sliding mode controller is a little bit more mathematical. Yeah, that is true, but it is very easy if someone has knowledge about basic circuits and these things, then it is not difficult to drive sliding mode control for any circuit. So this is the equation we can see here for boost operation from right side to left side, and this is the equation for buck converter operating stage for when power is being transferred from right side to left side. So now I will come to the simulation results. If our terminal device, which is like AND side converter AND side device, which demands 72 volt, then it means that our DC voltage, as I earlier mentioned, that was 48 volt. So the converter should operate in a boost operating mode. And since we are transferring power from left side to right side, so the boost stage is functional, and we can see that there is a very less, we can say, ripple voltage, and we get a steady state output voltage. This next one we will see load current. Here I have used a load of 25 ohm. So when we divide 72 by 25, then we get approximately this one. 24 volt. 24 ohm load is being used. So this is like that. Okay. And now we can see that mode transition, how quick the converter response is, we can see in this figure when we operating from left side to right side. We can see that converter response from boost mode to buck mode is quite fast. It approximately takes 2.5 or 3 millisecond. And this is current transition, and this is power transition, which is completely matching with the output voltage. So this is the buck mode in which we say consider that now our device doesn't require 72 volt. Our device demands for 24 volt. So this will step down the voltage to 24 volt because this is step up buck boost converter basically. So we don't need any other converter for this and this device. We can perform the same function with the same converter. So here also we can see that steady we get smooth output voltage and there is very less ripple voltage here. So now I will say that we want that our power should transfer from right side to left side. We say that now we want to charge the battery or something like that. So in this way, I have tried up to 80 volt as well. So here we say that our battery bank is of 60 volt. So we can see that output voltage is quite smooth. And if we reduce the battery level, for example, one battery is of 12 volt or something like that. So we say that we have now battery bank of 3 batteries connected, which are connected. We can see that here the output voltage is also quite fine. It means that it can charge different range of batteries which we have, battery bank or anything we have. So these are some few references which I mentioned in the introduction and topology selection and the reasons why we are selecting this one. That's all about this modeling and basically this is also can be called modeling and control of 4-switch buck boost converter based on sliding mode controller for bidirectional power, to handle bidirectional power flow. So thank you for all being here and listening to me. If you have any question, please you can go ahead.
Okay, so Qudrat,
Yes, Professor.
congratulations. Very interesting work, bidirectional system that you designed.
Thank you.
My question will be kind of similar to the previous one. So you are here a PhD student for about 1 year. So you have been traveling on this path of your PhD. Tell me how you feel that this course and this past experience made you a better researcher in power electronics. And how do you feel that this particular final project that you selected is important for you or is important for the PhD research that you are doing, please?
First of all, thank you for being our teacher. We learned a lot about power electronic solutions. We did not only learn about DC-DC converters in this course, we also learned something about inverters as well. And this course has been significantly important for me. And recently I was wishing that this course should, when I arrived here in the first semester, if I had taken that course during that time, I would have significantly more fast and advanced in my research in the previous 1 year. Because in this course is, I can see is important for me because I learned a lot related to converters and inverters and other some power electronics bases which we have forgotten from long time. And this final project is important because I hope that I am writing a paper on this final project. I hope that this can be published in a good conference or a journal. So this is significantly important for me. And the other inverter section was also important for me because my PhD research is mostly related to power electronics enabled advanced microgrids for distributed generations in which we are studying meshed grids, ring grids. I feel that this course has significant impact on my life and yeah, that's all.
Thank you very much. So let's give me an applause.
Thanks to you for being our teacher.
Okay, thank you. So I will just conclude here. Fine. So, as I said in the beginning, today is our last lecture. The master students who decide to just work on their project and upload the final project as a report, please do on Moodle. Moodle will be open until the guidelines of our university define that there is the time to submit the grade. So I will check that, but it's coming, okay? It's coming soon. So be aware that there is a cut. So do your upload of your required, I would say, work. Just to emphasize, you have 3 assignments, like 3 homeworks. You have a midterm project, and you have a final project. So just log in on Moodle and upload your reports. And as soon as possible, I will close the Moodle, close the course, and submit my grades. Okay. So thank you for all the attendance. And I will stop the recording here and just follow up with the class here who are present today. Thank you very much for this very successful semester and course that was taught for the first time here in our program. Thank you very much.